I will do my best. I'd like to start by thanking the organizers for accepting our paper and giving us an opportunity to speak about it at this lovely conference. It's actually my first AMS, and I'm very happy to be here. All right, so in this talk, we will be concerning ourselves with a function called the Mertens function. And the Mertens function is just what you get when you take the sum of all the values of the Mobius function mu of n for n up to a certain point n. So I've given an example here. I know we're all familiar with the Mertens function and the Mobius function, especially the Mobius function in this room. But I'm giving this example partly because I want you to see how much cancellation there is. So as you see, there's a lot of plus ones and a lot of minus ones, and a lot of them cancel each other out. And so it's kind of natural then to think that maybe there's so much cancellation that in absolute value, maybe this always ends up being pretty small relative to the size of n. So there was a conjecture by Mertens which said that if you look at the absolute value of m of n, that it's always less than or equal to the square root of n. Of course, now we know this is not true. So Odlyzko and Cirila showed that for some extremely large n, it ends up being false. But we don't know the first value of n for which this inequality fails. And so one thing that might be nice about computing values of m of n is one might hope that someday, eventually, with a lot more computer power and better algorithms, one might be able to find the first instance where this flips. We are currently nowhere close to that, so as far as we can tell. But anyway, that's one reason you might be interested in trying to compute m of n. Another reason you might be interested in this problem is that, okay, well, when n is large, asymptotic expressions are good. But when n is bounded, then computations are preferable. And so again, it's important to be able to compute with m of n for the kinds of ranges of values that we actually can think about. So the most naive thing you could possibly think of doing when computing m of n is just literally finding all the values of mu of n for values of little n up to capital N and just summing them all up. And of course, this is a terribly inefficient algorithm. So this takes time at least big O of capital N, the size of your range, times the average amount of time it takes to compute mu of n in that range. So this is not a great algorithm. And so my job today is to tell you how we can do better than the naive algorithm. So one way of saving some time is we could try to do something akin to the sieve of Baritosphines for detecting primes. So if you think about, when you teach elementary number theory maybe, and you tell your students about the sieve of Baritosphines, you have this table of size n, it's like a base square, and then you have students cross off, like the multiples of 2, multiples of 3, etc. So you can do a very similar type of thing in order to find the values of mu of n. And so if you do this, it takes time big O of n times double log of n, and it takes space big O of n because you have a table of size n. So one way of saving space is we could actually think of taking our table and cutting it into strips. So each row of the table becomes one strip of size square root of n, and you only have to think about the things of size square root of n at a time. And so this lets us cut our algorithm, the space consumption, down from big O of n to big O of square root of n. So that's just one way we could think of saving space in this kind of computation. But then one might ask, are there more ways of saving space? And the answer is yes. So if you really care a lot more than space as opposed to time, then you can use this algorithm that Harald came up with in 2020, which is an improved, a more space efficient version of the sieve of Baritosphines. And it lets you construct lists of primes up to n in time big O of n times log n, and space big O of n to the 1/3 times log n to the 2/3. And the thing about this is, again, if we compare with the previous page, we notice that up here we had n double log of n. So this one was a bit faster than big O of n log n. But we've gone with space from about n to the 1/2 down to about n to the 1/3. And so if you really care about space, then you use this one. And if you really care about time, maybe use a segmented sieve instead.
What does time mean here? Is it like arithmetic operations on numbers of size n?
Yeah.
So this is not like bit operations.
No, I don't think it's bit operations.
There are people that don't care about.
Yeah, sorry.
No,
You can hop in if you want.
Yeah, so the space is measured in bits.
Yes,
but
that's true.
The time is measured in word operation.
Yeah.
So it's closer to what happens to time.
The time is what we might think of as mathematicians as time, but yeah, spaces in terms of bit operations. That's a good point.
I mean, these things will be practical outside the range where you can use this for bit arithmetic.
Right. Anyway, so I just wanted to contrast these two things because in our results, we will give you kind of two versions of the same theorem. So one will be in terms of getting a better time allocation, and the other one will be using the Helfgott sieve to get something more space efficient, but sacrificing a bit of time. And so I wanted to show these two things just to say, this is where this disparity is coming from. All right. So now I want to give you a bit of history of this kind of problem. And so we have combinatorial methods. So there's basically going to be two approaches we look at, kind of combinatorial approaches and analytic approaches. The combinatorial approaches, the first steps were taken by Meisel and Lehmer, and then later there was work by Ligarius, Miller, and Odlyzko, and then Delaglise and Riva. And so all of these kind of use the same general idea, where you use some kind of an identity to break a sum of values of mu of n into shorter sums. And then you try to reuse the short sums as much as you can. And this gives us a time, in the Delaglise and Rival paper of about big O of n to the 2/3. So that's one sort of line of thought that's been taken in trying to work on these problems. But now I want to contrast it with the analytic methods. So these are due to Ligarius and Odlyzko. And so their idea is you can take m of n and you can write it as a sum over the zeros of the Riemann zeta function. And of course, there are infinitely many zeros, but one can truncate and round. And it turns out actually that if the error is less than a half, then it actually gives you an exact value. And so the time bound here theoretically is really good. It's all the way down to big O of n to the 1/2 plus epsilon. But in reality, this is maybe not the friendliest algorithm for computers to handle. And in fact, it's only been implemented for pi of x, the prime counting function, not for the Mertens function. And this was done by Platt in 2012, and it was really non-trivial to implement. And the other thing is it turns out to be slower than combinatorial methods in practice. And so what this means is that the big O constant is probably big enough that this is sort of throwing off things, even though theoretically it looks a lot better. But in the range that we're computing, that big O constant matters. So what Harald and I were interested in, so we wanted to stick to the combinatorial side of things. We wanted to make a better combinatorial algorithm, something that a computer could easily handle, but we wanted to improve on the previous time bound of n to the 2/3. So that was the number we were trying to beat. And we wanted to try to use as little space as possible. And so I will now tell you the two versions of our result. So we show that you can compute m of n in time about big O of n to the 3/5 times some log factors, and space big O of n to the 3/10 times some log factors. But this is the one that relies on the segmented sieve. And so this is the one, if you care more about time than space, then you use that segmented sieve and you get the results that I wrote in magenta. On the other hand, if you really care a lot about space, then you can use the Helfgott sieve. And then as you see, you get something a little bit worse in terms of time, but you get something all the way down to about n to the 1/5 in terms of space. And so it just depends on what your goal is. In our paper, we really wrote everything in terms of being time efficient, but we wrote some little comments in about how you could use the Helfgott sieve in order to get these space results. So I just wanted to put that there to sort of show the two flavors of our result. And then what I want to do for the rest of this talk is I want to tell you a bit about how we actually prove these things. So I'm going to start with just telling you in general how these combinatorial algorithms work, and then I'll tell you what we do differently. So in all of these, you take your big sum of m of n, and you use some kind of combinatorial identity to split it into shorter sums. And so we use the k=2 case of Heath-Brown's identity, but you could also use Vaughn's identity or Mobius inversion. You could just use something that splits a big sum into shorter sums. Then we do the usual analytic number theory thing where you see a double sum, so you swap the order of summation. And so that's how we get the quantity written in the box here. And we still have the same first term. Now, this first term doesn't matter because we can naively compute the sum of all the mu of n's up to the square root of n in time big O of the square root of n. So that one, we can just do whatever naive algorithm we want. But this is really where the focus in the rest of the talk is going to be, on how we actually sum things for this subtracted part. Okay, so now what we do, and this is what's done in all the papers before us. So in all these papers, you choose some kind of parameter, which we call nu, and we use it to split this range into two possible cases. So we first have the case where both M1 and M2 are at most nu, and then we secondly have the case where one of them, at least one of them, is bigger than nu. And so if you want to obtain time big O of n to the 2/3, as in Delagliese and Riva and the people that came before them, what they do is they take nu to the n to the 1/3. And then what this means is that the first case, the case where you have small values of M1 and M2, ends up being the easy case because you're not summing that many things just going up to n to the 1/3. However, the second case here takes a bit more work. And so that's really where the heavy lifting in the paper happens, is in handling that second case. So the first case, you just use a segmented sieve and it's quite straightforward. So anyway, that's what Delagliese and Riva and the people that came before them did roughly in their papers. What do we do differently? So we take nu to be a bit bigger. So remember that they took nu to be n to the 1/3, and we are taking it to be about n to the 2/5. And the way we actually get this value, it's not exactly n to the 2/5. There's again some fraction of logarithms in there. But we do an optimization at the end of all of our work, and then we end up coming up with this figure from the optimization. So anyway, that's approximately what we do. And then what this means is that now our cases are reversed. So the case where you have small values of M1 and M2, well, they're actually not that small anymore because they're going all the way up to n to the 2/5. So you have to worry a lot more about your sum, like as you sum things, taking too much time because you're just summing a lot more things. But the second case now turned out to be easier because you have fewer things to sum when you need M1 or M2 to be bigger than n to the 2/5. So the case is reversed. Now I want to say that this second case, it ends up being easier, but it doesn't follow immediately from Delagliese and Riva's work. So we end up doing similar things to them, but we have to be a little bit more careful. There's one place where they get something that ends up being big O of the number of divisors of n, which is log of n on average. And we actually can't have something that big because it messes stuff up later. So we have to get something that's big O of double log of n on average. And in order to get that extra savings, we use some lemma from the anatomy of integers. And we end up showing that when we have this recursion, that you can kill certain branches of the recursion because you get all this cancellation from the Mobius function and things end up summing to 0 anyway. So we just are a little bit more careful, but we basically kind of morally do what Delagliese and Riva do, just with a bit of extra savings. All right, so the rest of my talk, I want to tell you how we handle this first case. So what happens when your M1 and M2 are at most n to the 2/5? And I'm now going to change my notation on you because I hate having subscripts in the rest of my talk. So I'm going to call these little m and little n. And what I'm going to do is I try to compute this sum. Remember, this was the thing that was being subtracted after my combinatorial identities. This is the big thing we want to compute. I'm going to split this range into smaller neighborhoods. So I'm thinking of taking my box of size nu by nu, and I'm splitting it into neighborhoods, which I'm calling Ix and Iy. And you notice that as I've written here, these are centered at points little m naught and little n naught. So these are intervals of size 2a and 2b that are centered at specific points. And the reason I'm doing this is because I'm going to apply a local linear approximation now. And so that's what's happening on the right over here. We do a local linear approximation. And so we rewrite n over mn in terms of n over m naught n naught plus a constant times m minus n naught plus a constant times n minus n naught plus a quadratic error term. And of course, we always have to worry what happens with this quadratic error term. Well, it turns out it's not going to be a big deal as long as we take our neighborhoods u to be small enough. And so again, at the end of all this work, we have to do an optimization problem where we have to take our neighborhoods small enough so that our error terms don't affect things. But also we don't want to have too many neighborhoods to have to sum over. And so there again ends up being this final optimization that happens. All right, so if there were no floor functions in here, this would actually be a really easy problem. And I'm just going to tell you the fantasy version and then the reality. So the fantasy version is, let's pretend there's no floor. Let's pretend there's no quadratic error term. I'm just going to write in my local linear approximation that I had from the last slide instead of my n over mn, because we already showed that was a good approximation. And then what I'm going to do in the next line, where I've put a pink star, is you see that I've separated the variables. So I've written all my sums either over m or over n, but there's no interaction between them. And so this is nice because then we can just use a segmented sieve to compute values of mu of n or mu of n for the m's and n's in our two intervals. And then we just end up computing the sum, and summing these things together takes time, just the maximum of A and B, big O of the maximum of A and B. And so this isn't computationally expensive. So the upshot here is that this would be really easy if there were no floors. Unfortunately, we do have floors, and that's what makes it maybe a more interesting problem. So what we're going to do now is we're going to write down three sums. So we have a sum S0, which is actually equivalent in terms of the computation to the sum I had without floors on the previous slide. Because remember, on the previous slide, the whole point was we could separate the variables. The way that I've written this thing I'm calling S0 is I've written it so everything over m is inside one floor function and everything over n is inside another floor function. And so again, you're going to be able to separate these things out the same way you could before. So S0 is like the sum I wish I had. S1 is the sum I get via the local linear approximation. And then S2 is the thing we actually wanted to compute a few slides ago. That's like our real goal. And so what I'm going to do in the last 5 or so minutes of my talk is I'm going to show you how we can reduce the problem of computing S2 to computing S1. And it doesn't take that much extra time to compute S1 if you can compute S2, or sorry, other way around. It doesn't take that much more time to compute S2 if you can compute S1. And similarly, I'm going to reduce the problem of computing S1 to the problem of computing S0. So in each of these cases, I'm going to show that the sums are ending up being almost the same, and then it doesn't take that much time to get the difference between them. All right. So here's kind of the key idea. This is a basic fact from high school algebra. So if you take the floor of A plus B and you subtract out the separated version, the floor of A plus the floor of B, well, this difference is always either 0 or 1. And so it's going to be 0 if the fractional parts add up to something less than 1, and it's going to be 1 otherwise. And so what this means is that if you're looking term by term in those sums, S0 and S1, or S1 and S2, these terms almost always, they're either going to agree or they're going to differ by 1. So yeah, that's the difference between these terms. And so now I've written the terms in the sum. I've just called them L0, L1, and L2. So this is the terms we're summing in S0, the terms we're summing in S1, the terms we're summing in S2. And so our remaining goal is to show these differences can be computed quickly. And thus, since we can compute S0 quickly, and since we can compute these differences quickly, then we can compute the real sum we wanted, S2, quickly. All right, so what on earth am I doing on this slide? So on this slide, what I'm saying is, so far we've been thinking about this as a problem mod 1, right? Because we're thinking of things in terms of fractional parts and whether it pushes you over 1 or not. So rather than doing everything mod 1, I'm going to do the thing number theorists like to do, and I'm going to do everything mod q instead. So I'm going to convert this to a problem mod q, and it turns out that these differences of these terms, this L1 and L0 and L2 and L1, that these differences, they're going to, these two terms are going to be exactly the same in all but at most 2 residue classes mod q. So we're going to be able to throw out most residue classes mod q, and there's only going to be a few cases, you know, at most 2 residue classes mod q, where these things might actually be different from each other. So what am I doing here? Well, it would be kind of natural to take, for example, when we did our local linear approximation back here, it'd be natural to take something like the denominator of this to be our q. Unfortunately, these are actually pretty big, and so we end up wanting to take smaller q's. And so what we end up doing is a problem where we use continued fractions to do a Diophantine approximation. And so rather than having the C sub y that we started with, we're getting fractions a naught over q, where this q is smaller than whatever denominator we had here. And this is just easier for us to work with as we're solving this problem on mod q, where we're like looking at the difference between L1 versus L0 or L2 versus L1. So all this is saying is I can efficiently, in time about log of the size of my interval, find such an a naught over q, so that it's pretty close to the C sub y that I had from my local linear approximation. All right, so now the task is to show that these are almost always the same, except in at most two bad congruence classes. And the same is true for L1 versus L0. So I'm not going to get into all the details of that here, but we go through very carefully in our paper showing that indeed it's only going to be at most two bad residue classes where these differ. The other thing that we do in our paper is we end up showing that not only are there at most two bad residue classes mod q where these things differ, there's also only certain intervals out of our bigger interval where these things differ. So we're reducing ourselves not only to at most two bad residue classes mod q, but also only to certain intervals within our bigger interval that we're looking at values of mu of n and mu of m over. And so in the end, when we are computing the sum of mu of m, trying to look at the differences between these sums S2 and S1 versus S1 and S0, we only have to sum over a small number of things. So we're only summing over bad residue classes and m that live inside of bad intervals. So this gets rid of almost everything we would have had to sum. And so what this means is, in the end, you would expect something to take time about big O of A times B, but actually by getting rid of almost all of the residue classes and almost all of the intervals, we actually end up getting a factor, a savings, which is a factor of A. Remember, A and B are our two lengths of our intervals. So if we're summing things over M that are congruent to A bad and that are congruent to, that are inside this interval I bad, then you're getting a savings of A. So instead of getting a big O of A times B, you're just getting a big O of B for your time. And so there's this huge savings that happens because you're basically cutting out one dimension by showing that the disagreement can only happen in certain intervals and in certain residue classes. And so pictorially, what I'm saying is if you think about our big box of size x to the 2/5 by x to the 2/5, and then we're getting this savings of A, which is about x to the 1/5, that's the optimization we do at the end, trying to choose good sizes of our A and B, then what you end up getting is x to the 3/5 approximately as your runtime. And so this is roughly speaking how we get the stated time bound of big O of x to the 3/5. Of course, everything I've told you has had little extra log factors running around in it, which we've conveniently just swept under the table and ignored. So I'm not going to get into any of those details, but again, you can check out the paper if you really like suffering through expressions with lots of logs. What I want to end with is, especially because this is an algorithmic crowd, and a computational crowd, I wanted to show you what we end up getting when we use our algorithms. So Harald and I put our algorithms in C++ and we ran them on an 80-core machine at the Max Planck Institute for Mathematics. They were very generously hosting us for sabbatical time, and they let us keep using their computational power for like a year afterwards. And so what we ended up doing, you can see here, we extended Kuznetsov's work. So we were able to get an extra power of 10. And we were able to extend Hurst's work. So they each chose different values, like Kuznetsov did this at powers of 10 and Hurst did it at powers of 2. But in both cases, we were able to extend their work a little bit. And I want to emphasize here that we are not doing everything in a completely optimal way. So Kuznetsov and Hurst both go to a lot of work on the computational side, optimizing every bit of code, and we didn't do that. And so if you're someone who's interested in this, you could probably take our code and with some cleverness, push it further and hopefully get some extra values of M of n if you're interested. All right, so I am going to go ahead and end there, but thank you very much for your attention.